All right, so kinematics. We started talking about kinematics a little bit yesterday. Let's quickly just define that word. Didn't you guys, you studied all your Latin roots and Jesse?
We're gonna start about kinematics.
But you haven't learned those?
Let's not jump to conclusions.
Okay, all right. So what do you think, if we break this into parts, what do you think the kine part has to do?
Motion.
It has to do with motion, doesn't it, right? Okay, and I think that probably comes from like kinesis or something like that. Right? So that's motion.
Thing.
And then what's matics?
Study it.
Okay, so yeah, so now that's one I think study of isn't okay. Technically, I think it's called willing to. Mathematics really means willing to math, honestly. But you know, really, more likely we think of that as being kind of study of, right? So it's sort of, in this case especially, so it's study of motion, right?
Willing.
Or willing to move, I guess, I don't know. So, the kinematic quantities then, these are the quantities we use to describe very precisely motion, okay? We started talking about those yesterday. Position, I think we called it X yesterday. Let's go ahead and start calling it D, like the book does. If we're talking about motion on a line, you're free to call that X if you want to. What was displacement then? With a what?
Oh, it was delta.
Delta, yeah, delta. So it's change in position, right? So we'd say that maybe something like this. So delta D, we got the vector hat, 'cause it's a vector quantity, and it's D1 minus D naught, or D sub 0. What's the significance of D naught or D sub 0?
So it's starting again.
Okay, good. That's the initial position. Good. Okay. Before we go any further with that, I want to point something out that's sort of important. So let's go back to our model in the front of the room. We're just going to take simple motion in along a line, positive direction, negative direction. Okay, so where am I? What's my position right now?
Positive.
Okay, but give me a number. 2, you're right.
0.
0 is right also.
Yeah.
1. 5.
1, 5. Those are all right answers. Okay, those are all right answers. What's maybe the difference though? What's changing from answer? Let's just take 2 of them. Let's take 0 and 1 for example. The starting point. Okay, if we pick the answer to be 0, then that implies that my reference point or my origin, right, the 0 on the number line is here. If it's 1, where is it? Maybe right there, right? Does that make sense? Because I'm over 1 in the positive direction. Okay, so let's just be consistent here. For the moment, let's say we're calling this 0. Okay, so if this is my initial position and 2 1-meter steps this way, what am I at now? Negative 2, right? That's my position. What's my displacement from there to there? 2. 2? Negative 2.
Oh.
Right? How come?
Because you went to
Okay, it has a direction, and we're always going to say it's going to be the final value minus the initial value, right? Does that make sense? So my final value is negative 2 meters minus 0 is negative 2, right? Okay, let's go ahead and pick our other reference point. Let's say that this is 0, and I start at 1. Same story, though. I'm going to start at 1. I'm going to take 2 steps over here. Where do I end up? Negative 1. What's my displacement? Negative 2. Negative 1 meter minus 1 meter. My starting position would be negative 2. What's the moral of that story? An important moral to that story I just told. What happened? I moved the same.
They're not the distance from the starting point and displacement are not overall.
Okay, so the positions could have varied depending on where we wanted to measure it from, right? But what was the same both times? Displacement was the same. Regardless of how I chose to identify or label my positions, the change in position was the same each time. That's really significant. Okay? Did you get that? Okay, so it really doesn't matter. It's arbitrary where we would choose our reference point, but if we're talking about motion relative to let's say any fixed reference point we choose in the room, it doesn't really matter. As long as the reference point is gonna be at rest, let's say relative to the room. And we'll get into this stuff more in future chapters. It'll give you just a glimpse of what's coming up here. See if you can kind of reconcile this. As long as the reference point is not moving itself, then any motion that I measure relative to that reference point is not gonna matter, right? The individual positions do, but the change in position would always be the same. You kind of see that? We'll see it at the next level when we start talking about vectors, right? Right now, it's really simple to see because all our motion is just on this single line up here. And so vectors are simple. Vectors really are just numbers, right? They're just numbers with a sign, +1, -1. Later on, we move into 2 dimensions or even 3 dimensions. It's a little trickier, right? Because now the vectors don't all point just either this way or that way, but the result is going to be the same. So just kind of hold that thought for a while. We'll get back to that later. Okay, average velocity. How do we define that? Yeah, just displacement over time, right? So change in position or displacement divided by time, okay? And that's, okay, so let's say that we're gonna travel to Portland. Portland is, I don't know, say where we're going is 200 miles away, let's say, okay? But there's some construction going on and our path is a little bit, or from here to there is not just consistent. We can't just put the cruise control on. We gotta speed up and slow down, and there's some obstructions along the way. Let's say it takes us 4 hours to get there. What's our average velocity? 50 miles an hour. Right. Total displacement is 200 miles, right? Let's just assume. And it takes us 4 hours to get there. So our average velocity is 200 divided by 4 is 50, right? 50 miles per hour. We could maybe talk about that in terms even of speed instead of velocity, because maybe, I don't know what the displacement really is, because you don't travel a totally straight path. But let's just say that we travel a total distance along the road of 200 miles. Then instead of calling that average velocity, we call it what? Average speed. Okay, make sense? Does that mean that we were going 50 miles an hour the whole time? No way. Does it mean we were ever going 50 miles an hour even very often? Probably not. We're probably either going much slower than that when we're, at some kind of obstruction, or faster than that when we're traveling freely, right? So when we talk about an average quantity, take velocity for example, it really only depends on what? Does it really tell an accurate story about what's happening along the way? No, it's really just telling us
Where you start, where you stop.
yeah, it really only depends on kind of the beginning and the end values, right? Does that make sense? Okay. And we had a kind of a weird example of that yesterday. If I start here, let's say I start here at -1 meters, and I'm gonna walk up here and pause for a second, maybe I'll walk up some more, and then I walk back over here, and I end up at -1 meters again after 10 seconds. What's my average velocity? 0, right? Because I start and stop, or begin and end at the same place. Was my average speed 0? No. I didn't give you the specifics, so you couldn't calculate it, but it was something, right? I did cover some distance in 10 seconds. Agreed? Okay? If I were pushing one of those wheels, that you use in track to measure out distances, if I had pushed that the whole way, we could have looked at that to determine how much distance did I actually cover, and then I could have divided that by 10, right? Okay. But maybe there's something else we'd like to know. So average velocity is useful because it might make a prediction if we were going to make the same trip next week and we wanted to be able to tell our buddy he's going to meet us in Portland, well, okay, I'm going to leave here at 1, so you probably want to meet me there at 5, right? Because that's what our average velocity predicts. And that's a good tool for something like that. But if I wanted to be able to make a prediction of maybe how fast I'm going to be driving by, I don't know, some landmark on the RU elevator along the road, that may not be the best tool for that. What would I probably do instead if I wanted to kind of get an idea of how fast I'm going down the road by route elevator, what would you do? Where would you look? Your speedometer, probably, right? And that's gonna be much more accurate. Right as I go by, if I look at my speedometer, I'm gonna get a pretty accurate measurement of how fast I'm going. Is that measuring average velocity? What do you think we would call that? Current velocity, maybe? So the velocity at that moment? I want to think of the term we might use in physics. Specific? No, it's not like that. It's not the one, not the right answer, but it's a good answer. It's not a velocity over an interval, it's a velocity at that instant, right? So it's instantaneous velocity, okay? Instantaneous velocity can change with time, right? And we could have two completely different profiles of our trip from here to Portland, but still end up with the same average velocity, right? Okay. We usually just denote that with a plain old vector v. That's different from the v bar, right? The bar indicates it's an average. Okay. I'm not going to be very good about remembering to always write that stuff down, so please call me on it, because I guarantee I'll forget. That's instantaneous velocity. We'll talk more about that later. As we start to get into the class a little bit more and we get further with kinematics, one really nice thing about this is, and this will apply to, how many people have, well, I got some people in calculus. I assume nobody took calculus last year, right? In here? No, that's fine. So even if you're not in calculus now, it's nice if you are, in a way, because it's going to illustrate some things that we're talking about in calculus. But even if you're not, here's the real bonus of this. You're probably going to take calculus like next year or the year after if you're not taking it this year, right? Likely. This is a really good way to illustrate some stuff that's going to come up in calculus, some quantities. So when we get there, I'll kind of fill you on that, but that's for later. Okay, so we got to go one step more though. So when we talk about kinematic quantities, we talked about position, right? We talked about velocity or speed. Let me ask you something. If you are, okay, here's the scenario. You got to kind of imagine this situation. Say you're in a car, and the car is a really smooth riding car. So you can't even tell if the car is necessarily moving down the road or just at rest, because it's such a smooth car. It's a really nice, smooth, newly paved stretch of road. Straight section. If you're in the car and you wake up from a nap in the car and it's completely dark, maybe you've got your blinders on because you didn't want to be interrupted, you're sleeping. Can you tell immediately if you hear the purr of the engine? Can you tell if you are moving down the road with cruise control on or at rest? You really can't, can you? You can't, right? They feel the same. Now, what could happen, though, that would give you an immediate idea if you were moving or not? So, okay, well, I heard lots of things. If there's a little jolt in the car, okay, meaning that maybe you turn a little bit or something, okay, you turn, or change directions by turning, okay, what else could happen?
So one of the things that would help, it's dark though.
Those would work, you'd feel that, right? Changing speed. Yeah, if you were to speed up, that would feel like something, right? If you were to speed up, you would feel compressed against your seat, right?
Yeah.
Or if you put on the brakes, you'd feel like you were constrained a little bit by the seat belt or something, right? Okay, so it's not position. We can't sense position. And it's not velocity that gave you that cue. What's the quantity that gave you the cue that you actually were moving? What do you think it is? Yeah.
Inertia. It's like your inertia.
Okay. Your inertia is changing, and we'll hold that thought for like chapter 5 or something. That's good. But there's a kinematic quantity. Without thinking about forces at all, there's something that we can sense. Okay. It has to do with a change in speed. So what we're getting at here is there's another kinematic quantity we want to define. Acceleration. Yeah. We can sense acceleration. That's the one kinematic quantity that we do. That's It feels like something. The rest of this stuff doesn't, right? Okay, so average. Now, I put average in parentheses because in this class, we are seldom, if ever, going to deal with situations where the acceleration is changing. And we'll talk about it a little bit, but in terms of, we won't deal with it very often, okay? So when we talk about average acceleration, we might as well just call that acceleration because our acceleration is almost always going to be constant anyway, okay? Does that make sense? And so here's technically the formula for average acceleration, or for us, just constant acceleration. Yeah.
Is there not a bar above A as well?
Okay, so that's what I'm saying. I mean, if this were maybe a college calculus-based physics class, then we'd have to distinguish between the two because we would be treating situations where acceleration was changing with time. We won't really do that though. So for us, rather than have to write the bar every time, average acceleration is really the same thing as acceleration because it's a constant, right? Does that make sense? So technically it's average acceleration, but we're gonna keep it constant anyway.
So it's different than velocity. Velocity has specific average.
Right, but for us, velocity is different though, because when we talk about accelerated motion, we'll start to talk about that today a little bit. Accelerated motion means that the velocity is changing, right? Does that make sense? Okay, so this is the definition of acceleration, then. Acceleration is equal to the rate of change of velocity. Okay, I want you to notice something here. There's kind of like a food chain in kinematics, right? There's a corresponding relationship between velocity and displacement and acceleration and velocity, isn't there? Does that make sense? So acceleration is to velocity as velocity is to position. That's not going to be incredibly meaningful to us now, but it will pretty soon. We'll start to be able to look at some parallel relationships there that may give you a real intuition about physics, about motion. Okay. All right. So let's explore this acceleration thing for just a little bit. Let's look at this. Let's take an example like this. Okay. So we're going to go back to one of those motion diagrams like we talked about yesterday. We just kind of barely talked about. Remember the dots? If the dots are, if we're going to take pictures of an object's motion with time, think of those as being kind of the frames in a movie. The further the frames, the object is apart from frame to frame, the faster it must have been going, right? Does that make sense? It covered more distance between second 3 and second 4 than it did between second 2 and second 3. See what I'm saying? So that must have a higher velocity there than there, right? Okay. So then what do those vectors represent? Those red vectors? What do you think? What do you think those vectors? Velocity, right? Everybody see that? You see how that matches? You see how this is saying a bigger velocity than that? How come? What about the arrows telling us that? Yeah, the magnitude, right? We said velocity or vectors have two parts. They have magnitude and direction, right? Magnitude is a number. We represent vectors with arrows, and the way we represent the magnitude is the length of the arrow, right? The longer the arrow, the greater the magnitude of the vector. Obviously, the arrow's pointing in a direction, and so the direction part's pretty obvious, right? But here, it's moving to the right faster than it is there, because the vector's longer. Agreed? Okay, so then what if we were to just kind of focus in on these two vectors? Let's just take this brief interval of time from 2 seconds to 3 seconds, okay? So over that interval, if I'm just going to kind of only consider that 1 second interval, isn't that my initial velocity? And that's my final velocity, right? Okay, well look at this then. If we blow those up a little bit, my initial velocity and my final velocity, there's a difference between the two, right? Final velocity minus initial velocity. If I subtract this initial velocity away from my final velocity, don't I have about that much left over? Right? Does that make sense? So that's the change in velocity, and it's only a 1 second interval, right? We defined acceleration as change in velocity over change in time. So it's going to be that much of a difference divided by 1. Get the idea? This is really just intended to be kind of a visual representation. But that's giving us some acceleration in that direction, right? How come it's in that direction?
Because it's accelerating.
it's accelerating, it's because my velocity in that direction is increasing. Does that make sense? Acceleration is the rate of change of velocity, change in velocity over change in time. Well, the velocity is increasing in that direction, so we call that a positive acceleration, right? It's adding to my, I start off with a small positive velocity and I end up with a larger positive velocity. So the change in velocity over that time interval was positive. Agreed? Okay, what about in the middle? Right in here, what do you notice about all three of those vectors? They're the same size. So is the velocity changing from second to second? It's not. And so the initial velocity and the final velocity vectors would be the same, right? And so how much of a difference is there? None. So the acceleration is 0, right? Make sense? What about over here? If we look from second 7 to second 8 at our velocities, well, I'm slowing down, right? My initial velocity would be there, and my final velocity would be there, correct? Let's compare those. Initial velocity, final velocity, well, what did we do? Yeah, we decreased the magnitude of the positive velocity. So does it make sense that the acceleration is negative there?
Yeah.
Right? Isn't it true that if we change from, let's just say arbitrarily that this was 10 and that was 6, if we change from positive 10 meters per second to positive 6 meters per second, well, we lost 4 meters per second, right? Make sense? Okay, so I want you to tell me then. True, false. Here's my story. I'm starting right here at rest, at 0, and I'm going to walk this way and pick up speed, so when I get to here, after a couple seconds, I'm moving pretty fast in that direction. Okay? Acceleration is positive or negative? Okay. Am I accelerating or decelerating? I'm accelerating. Okay, good. It makes sense. Positive acceleration, acceleration. Okay, let's try something different. I'm going to start here, and actually let's do something different. I'm going to start here now. We're going to start the watch when I'm already moving. I'm already booking by here pretty fast, right? You have a great running form while I'm doing it. And I'm going to start the stopwatch, and I'm going to put on the brakes and slow down. Okay. So now what happened there? Okay, what's the sign of my acceleration? It's negative, isn't it? Right? It's negative because my velocity went from a high positive value to a low positive value. Agreed? And I slowed down. Okay, so that's deceleration, right? Everybody agree? Let's try a different one. How about this one? What if I go, I'm going to start here at rest, and I'm going to pick up speed in this direction. After a couple seconds, I'm going pretty fast in that direction. Okay, what's the sign of my acceleration?
Positive.
How come? Okay, but isn't acceleration defined as the change in velocity or change in time? So what do you think?
Yeah, so you just change your direction.
Okay, but now hold on. If my velocity here is 0 or small, but negative, right? Let's just say I'm going pretty slowly. So I got negative 1 meters per second is my velocity, because I'm going in the negative direction, right? Let's do the math here. I speed up, and let's say by the time I get here, I'm going 5 meters per second in the negative direction. So that's negative 5 meters per second, right? So let's calculate acceleration. My final velocity is negative 5 minus my initial, which is negative 1. What's negative 5 minus negative 1? Hang on. Negative 5 minus a negative is like adding, right? So negative 4, okay, divided by, let's say it's 2 seconds. It takes me 2 seconds to do it. So my change in velocity is negative 4 meters per second, divided by 2 is negative 2. So my acceleration, the equation tells me it's negative. And it is. Does it make sense? How come it's negative? Because I'm increasing my velocity in the negative direction. Okay. Wouldn't you agree that increasing velocity in the negative direction is the same as decreasing velocity in the positive direction? Does that make sense? So do you see that really the first example I did, I think that's the one where is it? Hang on. The second one, where I was moving pretty fast and I slowed down, right? That's really very closely related to the third example, where I start slow here, and I pick up speed in that direction. In fact, if I continued the trend of the second example, right, if I continued, I didn't stop the movie, if I just continued with constant acceleration, negative acceleration, wouldn't I just do this, going fast, slow down, stop, start picking up speed in that direction?
That makes more sense.
Right? You see what I'm saying? We just looked at two different segments of the same movie, right? You get that? If I throw a ball up in the air, what's it do? It comes back down. It leaves my hand going pretty fast in the positive up direction, right? It loses speed on the way up, and then it's going to gain speed on the way back down. Okay, did gravity flip a switch when I got to the top? No. As we'll talk about soon, the acceleration of gravity is the same. It doesn't change. It's the same, it's constant, and it's negative, right? It's trying to either decrease the positive acceleration of the ball or increase its, to the backwards. You gotta be careful with what I say. Trying to either decrease the positive velocity of the ball on the way up or increase its negative velocity. Same dip, right? Okay, how about this one? Now think, this is tricky. This time I'm gonna start moving pretty fast in that direction, okay? I'm going pretty fast, and I slow down with time stop. I'm going slowly in that direction. Now think about this. Think about this for a second. I wanna know, don't say it out loud, I wanna know what's the sign of the acceleration, and is it acceleration or deceleration? Oh, by the way, we didn't answer that. On this one where I started slow and picked up speed, it's negative acceleration, but was it acceleration or deceleration? Tricky. I mean, the answer is, and this is why I hate the word deceleration. The answer is acceleration, because acceleration really should mean speeding up, and deceleration really should mean slowing down. It's confusing though, isn't it, right? And so we want to use those words as cautiously and as sparingly as we can, right? So one more time, back to this one now. So now I'm starting off going fast, and I slow down with time, moving in that direction. Okay, what do you think? Positive acceleration. How come?
Because it's deceleration in the negative.
Okay, you've made that connection, sure. It's positive acceleration because if I think about the change in velocity, I'm starting with a big negative velocity and ending with a small negative velocity. Let's just attach some numbers to it just so it's easier to deal with. Say I'm starting off at negative 8 meters per second, and I end up at negative 2 meters per second after 2 seconds. What's my change in velocity if I end up at negative 2 and start at negative 8? Positive 6, right? My final value is negative 2 minus negative 8. It's like adding 8, right? Does that make sense? So we actually, our velocity increased by 6. So I went from negative 8 to negative 2, right? Divided by 2 seconds would be what? Positive 3 meters per second squared? Meters per second per second. We haven't talked about units yet. Without dealing with units, the number of the acceleration would be positive 3, right? Agreed? Okay? But I'm speeding, what was I doing? I was slowing down, so it's deceleration, right? Here's kind of a little model to help with this. You probably got it, but just in case, imagine an invisible hand that's pushing on me to affect the change that I described. And honestly, this is going to make a lot more sense in a little while, because as we're going to find, force and acceleration are intimately connected, right? But if I'm starting off fast and getting slow, isn't that invisible hand pushing me in that direction? That's the positive direction, right? So it's positive acceleration. See what I'm saying? Okay. If I'm starting off slow and picking up speed, well then the hand is also pushing me in the positive direction. If I'm starting off fast in the positive direction and slowing down, well that hand is resisting me and pushing me back that way, right? So the sign of the acceleration is negative. Does that make sense? Just a little tool, kind of help you with that. Right? Get the idea? Okay. Let's talk about units for a second. So we know what the units of our standard, we talked about units, that was before round, it's been a while. We talked about standard units for position or displacement being what? What's our base unit? Remember we talked about units, when we talk about standard SI units in science, we mean, another way of saying that is MKS units. M for
Modern.
meters, S probably for what? Seconds, and K for kilograms. Okay, so which one of those is going to fit well with position or displacement? Meters. Measure that in meters. So what's velocity or speed going to be measured in that? Well, meters per second, because look what the formula is, right? The formula is units of displacement, right? So that's going to be meters over units of time, seconds. So meters per second, right? Make sense? Okay, what about acceleration though? Ah, that's weird. I got units of velocity, which is that. So meters per second divided by seconds. So technically, the unit of acceleration is a meter per second. Okay, but there's a better way to describe that. If we think about this mathematically, just a little bit here, what happens, I could make the bottom into a fraction, right? We're just dealing with the units here now, right? This is called unitary analysis, or dimensional analysis. And it's just a fancy word for just seeing what the units do. So if I divide a fraction by a fraction, what do I do to the bottom fraction? Okay, I've got flip and multiply, right? So I'm going to multiply by the reciprocal. So that's the same thing as saying meters per second times 1 over seconds, or per seconds. Okay, well, when we deal with units, we always just treat the units like variables, right? When we do any kind of arithmetic with them. So what would I do if I multiply fractions?
Just multiply.
Multiply straight across, right? So I'm just going to get meters per second times second is a second squared. Okay, so our units, the way we describe units of acceleration the most efficiently, we would just say we always do it in terms of meters per second squared. Meaning, though, really, meters per second. Okay? Make sense? All right. How are we doing for time here? Oh, a little time. Nice. I think we're pretty good for yeah. I wonder if there's anything I want to throw at you. I think let's try a couple. I want to give you a couple formulas. Might as well give them to you today. You could start on the assignments in if you want to. Let's come up with just a couple kinematics equations, and they're even in your book. I'm gonna give them to you, and you kind of tell me if they make sense. If we go back, we don't get very many of them. In fact, really, all we get, I think, next chapter, we get into a lot more of this stuff. Okay, here's one. Okay, doesn't this make sense? I mean, really, this is a pretty hokey equation in a way, because that's just taking the definition of average velocity and solving for delta D, right? But it's helpful. It does give us a little different perspective on those quantities. So if we say that, what's the definition of average velocity again?
Reaching position and reaching time.
Yeah, good. So displacement over time. If I solve for displacement, I just multiply both sides by delta T, right? Everybody agree? And so that gives me displacement equals average velocity times time. And usually delta T is a little bit almost redundant because when we start the stopwatch, what's the value of T? Well, but usually that would be where we'd set time to be 0, right? So T final minus T initial is always just time minus 0. So saying delta T is really just equivalent to saying T, the time of the event that we're watching, right? Okay. So there's one equation. Displacement equals average velocity times time. Okay. What else do we get? Well, we get another one. Oops. acceleration, okay, we got that right. If average acceleration equals change in velocity over change in time, what if I solve that for example, change in velocity? Let's see what we can do with that. So, acceleration, or average acceleration, equals delta V over delta T. Okay, if I solve that for delta V, sorry, doesn't this just give me delta V equals a T? And what is delta V? Delta V is just really final velocity minus initial velocity, right? Okay, usually we say V1 minus V0, but let's just call it V for the final velocity. Just call it V. So that's going to give me V minus V0 equals AT. But wouldn't it be slick if we could just solve for our final velocity in terms of our initial velocity and our acceleration and our time, right? Well, we have it. All we can do is add that term to the other side, and we get another kinematics equation. V equals V0 plus AT, right? So let's try that one on for size. Write it down. Okay, let's say we got a car that when we start the stopwatch, the car is traveling in the positive direction, and let's say that its initial velocity is 10 meters per second. It's accelerating at a rate of 4 meters per second squared. And we're going to let this thing accelerate for a time of 3 seconds. Can we predict how fast the car is going at the end of that 3 seconds? There's our model, right? We see that? All we got to do is plug in these values, identify what they are. Well, that's V0, right? So we're going to get 10 meters per second plus, what's my acceleration? Positive 4 times time, 3 seconds. Well, what do we get? Okay, well, we just get 10 meters per second plus. What happens to my units here if I multiply meters per second squared times seconds? Yeah, because that's like a second over 1, and so I could cancel one of those, couldn't I? Just like in algebra, if I had an x over an x squared, that's algebraically equivalent to 1 over x, right? It's the same thing as saying x over x times x. Well, I can cancel like factors, right? We have a property of exponents. We can say that we could just subtract the exponents, right? When we divide like bases. I could write this if I wanted to. If you want to think about this in terms of the properties of exponents, that's the same thing as saying x to the 1 minus 2, right? Everybody agree? X to the minus 1. Isn't x to the minus 1 just 1 over x? Or, in my algebra classes, I always tell people there's an alternate way to do this when it's convenient. What if the power on the bottom is bigger? Then I could just subtract the top exponent from the bottom exponent, right? So I get 1 over x to the 2 minus 1. Either way, it's just 1 over x. So, moral of the story being that I can cancel that second with one of those seconds, and look what happens then. It has to work this way, doesn't it? Because then I get 10 meters per second plus, what's 4 times 3? 12 meters per second. The units have to be the same, don't they? I couldn't add them up because they didn't have the same units. It makes them like terms. And so we end up with our answer being 22 meters per second. Make sense? That's kinematics. We're going to use some relationship among the kinematic quantities and the kinds of problems you're going to be doing on the problem set that's actually up there now, is you're going to be identifying what quantities are given to you and what's the quantity that you're trying to find, and then just plugging in the quantities you know and getting an answer. Okay, what about units? You're probably expecting me to tell you that it's really important to always include units so you can see if they work out. Oh yeah, okay, yeah. I mean, it's not a bad idea. You can, by including units, if the units work out, you can be not guaranteed, but at least somewhat confident you did it correctly. Bottom line, physicists never do that. Physicists don't include units because it's a lot of writing, and it gets messy. And so, once you get the hang of that, I think it's fine to say, okay, I know I've expressed everything in terms of standard units, right? So if I plug it into this equation and I'm starting with standard units, I'm gonna get a number back in terms of standard units. What should the units of velocity be? Meters per second, so I'll just tack a meters per second on the end. And not ever have to really worry about what these units were the whole way, as long as they're standard units. Does that make sense? We call that suppressing the units in physics, and it's a license to be a little bit lazy.